In the third chapter, we continue now with the process of creating a model. It's already been described that there are different levels of complexity of a model. In the following, we show a very basic case how we can add details to a model and defining our own formal model, and thus explore how we can decide on our own about the level of complexity for our own model. Before we start modeling, let's recapitulate the reasons why creating good models is important for you. Beginning of the final crisis, there was the decision which bank the US government should let go bankrupt. Finally, as most of you may know, they decided for Lehman Brothers because their model that they created for making this decision predicted that this bank has the fewest links to other banks, means the fewest business contacts. Therefore, the assumption was that the net effect is minimized by selecting this bank, so that the effect to other banks may be not that dramatic than by choosing another bank. Nevertheless, as we all know, the effect on the global financial system was much more complex, and therefore the consequences were very difficult to predict and led to unforeseen consequences in the following years. Only today, afterwards, after this decision was made, we are able now to realize how complex it was, and we know the full consequences of this individual decision. But nevertheless, it's a very good idea to base your decision that may have a dramatic effect on a model that is as good as possible. Now, there is a very nice and provoking quotation, which is always important to remember in the following, and always if you use models, which says, essentially all models are wrong, but some are useful. And that's exactly what the whole lecture on model theory is about. That's that you're able to understand how you create models and how you define for yourself which models are useful and how many details you have to include into them. And that's what we will look in this section as well. And this quotation is that nice because a model represents, of course, only a part of the reality. Therefore, it's wrong by definition. So all models are wrong. But smart people don't blindly do what the model tells them, but they use them to support their thinking, to gain insights or support their decisions just by adding additional arguments for a more complex kind of decision or during a decision-making process. The most important phase for creating a model is deciding which parts of the real world shall be represented by our model in the model world. Therefore, you need to define the purpose of your model first. The restrictions you may face are the available resources for building your model. This can be time, money, employees, some kind of information that you need for your model. So they also define how many details you can represent in the model world. There is the nice analogy of Occam's razor, which expresses a philosophical principle, which says that you should not use more things that are necessary for an explanation, or in our case, for a model. So restrict your model, restrict your explanation to the most important elements, the most important things that are really important for your model, that expresses or that includes the key mechanisms, the key features, but not more. So the model will not become better if you include more, it will become worse. This idea was formulated by William of Ockham, why it's called the Ockham's razor, in the 14th century. There is a nice exercise from the book How to Model It, Problem Solving in the Computer Age, which we now use just for increasing our understanding of this modeling process. So please try to follow the instructions of this exercise as close as possible for your own insight. Look around you, estimate the size of the room, and now the task of this exercise is that you try to figure out how many ping pong balls could fit into the room in which you sit. You have 60 seconds to answer these questions. For this time, I pause the video and tell you when the 60 seconds are over. Now the 60 seconds are over. Please write down the number of ping pong balls that you think can fit into the room in which you sit. You can also use the comment box below this video to remember the number, and please also add the room for which you made this estimation, because maybe you do this in a computer pool where other people are sitting, so you can compare your own estimation with the one from your neighbor or from others that have done this exercise as well, just to enjoy the very broad range of different estimations. In the next step, we increase the resources that you have to solve the same problem. So we just increase the resource time that you get to solve the same problem as before. So how many ping pong balls fit into this room in which you sit? Edit the question within the next 5 minutes, and please pay attention to how you solve the task. If possible, collaborate with a neighbor that you may find or who is watching the same video, and pause the video and try to work together on this task. If not, it's not a problem if you do it on your own. I pause again the video for 5 minutes and tell you when the 5 minutes are over. Now the 5 minutes are over. Please write down the number of balls that you've estimated this time. Ideally, use again the comment box below to remember the number and add the room for which you made your estimation. Maybe you came up with a symbolic representation of the solution. Such a solution could look similar to the one shown on the slide. So a very simple kind of formal model that helps you to find a solution, which is somehow obvious to build this kind of model if you have enough time. So the representation could be that you use a variable L for the length of the room, W for the width of the room, and H for the height of the room. And then you can calculate the volume of the room by multiplying the three variables. And finally, you need to estimate the volume of a ball. You could make a simplified representation of the ball by a box, which is simpler to estimate in terms of the volume. So length, width, and height of the box. And then all you need to do is to divide the volume of the room by the volume of the ball. And this gives you the number of estimated balls that fit into the room. If you have more time, you can make the result more precise by subtracting the furniture, the volume of the furniture in the room, and so on and so on. So you can add more details to get a more precise result. Now, finally, you may ask what you can do with these modeling techniques that I've shown you in this lesson for architecture or urban design. Since formulas and models of the exact sciences that are more related to these models, they may not be appropriated for us as designers or planners. But what about the design models? In the field of computer programming and engineering, design models are well known. In this environment, they consist of a document consisting of a list of requirements formulated to reduce the range of options for implementations. These design models often take the form of a handbook, illustrated with organizational charts containing checklists that help the programmer to structure this process. So there is a similar approach by Christoph Alexander, who formulated the pattern language, which was also an approach to collect a lot of sample or pattern solutions for specific problems. They are linked with each other to help planners and designers to find the right solutions and the right process of solving more complex problems. This idea was also used by computer programmers to develop this object-oriented programming paradigm, where you also have kind of patterns or pattern-oriented programming, which is a similar approach, representing solution patterns for problems that you may have while solving a problem in programming. So I'm convinced that these techniques that we explore in this module can help you for solving design and planning tasks, and especially when combining them with computational tools, and what the whole seminar is about.